Hello, welcome to today's seminar. Thank you for coming in the middle of the summer. We have a visitor, Jan Volec from ETH Zurich. He got his PhD with Dan Kral at the University of Warwick, and he will be talking about fractional coloring of subcubic triangle-free graphs.
Okay, thanks Bernard for the invitation. Thanks to all of you for showing up in the off-term time. So, yeah, as Bernard just said, and just talk about, my talk will be about fractional colorings, and I will try to, before I will exactly describe the problem we were working on, I will go through some motivation, and also I will make precise what I mean by triangle-free, what I mean by subcubic, maybe what I mean by graphs, and also what I mean by fractional chromatic number. And before I start, let me also say that all of what I'm going to talk about today, it was a joint work with Zdenek, who is in Prague, and with Jean-Sebastien Sereni, who is in Nancy in France, and who was actually my PhD co-supervisor. Alright, so before I move to the problem we are interested in, let me recall some history and motivation for like the big bunch of questions that like my problem will follow. So it somewhat all started, well, the whole graph coloring area started with the four-color theorem, but also the fractional colorings, the notion of fractional colorings started with the four-color theorem. But so now it's a four-color theorem, and it was proven in 1977 by Apple and Heckman. But sometime before, like before 1977, people were not sure whether four-color theorem is true or not. So they were also trying to come with some weaker notion that would be like a corollary of four-color theorem, and try to think about that. So, but anyway, so what is four-color theorem? It says that whenever I have a political map, and let's say I avoid enclaves and exclaves and whatever weird things that are in the real life happening, so whenever there is a country, it's just a consecutive area, then I can take 4 pencils and fill in the political map using those 4 pencils such that no two neighboring countries will have the same color. So, for instance, if I zoom just at one continent, which might be Africa, if I'm not mistaken, and I look there, every 2 neighboring countries have different color. How do I translate it to a graph theory language?
It seems to me that on the bottom there are 2 yellows touching each other. Is it one country?
I think there is this big filling with purple and
purple pixel. Okay.
And that so maybe just the scaling is not good. Anyways, I hope that you got the picture modulo some pixel perturbation. In the worst case, I will color it red and it will be. Oh. So anyway, so what I wanted to say, so how do you model it in a graph theory language? Well, you put in every country you put a vertex, then 2 neighboring countries you will join by an edge, and the graph that you obtain from a political map will be planar, and then the statement is that planar graphs are always 4-color. So a particular corollary of 4-color theorem is that every planar graph has an independent set of size at least n over 4. Just take your largest color class. And this statement itself, every planar graph has independent set of size n over 4, is also sometimes known as the R-Wissing conjecture. So now, not a conjecture anymore. It's a corollary of 4-color theorem. However, there is no proof, no other proof than just proving 4-color theorem and then saying, oh, a corollary of 4-color theorem is the R-Wissing. That is that's the only way what we can do so far. And it's still interesting. So one thing is that all the known proofs of 4-color theorem are computer assisted. So there is still lots of effort of finding like computer-free and just human checkable proofs of that statement. And in particular, there is also still some effort like finding a proof of R-Wissing conjecture that would avoid using computers. And the best result in that direction is a very recent result of Cranston and Rabin, who proved, okay, so you would like to show at least 3 over 12, well, they can show at least 3 over 13 as the independence ratio. So let me state another corollary of 4-color theorem, which will lie somewhere in between the R-Wissing conjecture and the 4-color theorem. And let me call it a fractional 4-color theorem. So there are plenty ways how to state fractional four-color theorem. But one way of stating it is saying that, okay, so you give me your planar graph G, to each vertex you place a weight, and now you would like to find an independent set that has at least 1/4 of the total weight. So if all the weights are uniform, I'm back in my R-Wissing conjecture, but now I would be maybe preferring some vertices over another ones, and the fractional four-color theorem says no matter how you put your weights, you always can hit at least 1/4 of the total weight. And why is it a corollary of four-color theorem? Well, for the R-Wissing conjecture, you just take the largest independent set. This time you would take the heaviest independent set, the heaviest color class. So we have 4 color classes, at least one of them, and they cover all the vertices, so at least one of them must contain at least 1/4 of the total weight. So, yeah. And of course, this fractional four-color theorem says that it should work for any assignment of weights. So if I put there uniform weights, I'm back in R-Wissing conjecture. So like the four-color theorem implies both of these results, and the fractional four-color theorem implies the independence. So, is that so far okay? Are there any questions? If not, then let me maybe make this. Let me make more clear what I mean by fractional coloring. This time of a general graph G, and also like maybe like this weighted independence set. I said that it's one way of defining fractional chromatic number, but maybe let me also define it in a few different ways, and those different ways will be maybe more graph coloring like. So another way of defining one way of saying of defining a fractional, what a fractional coloring is, goes as follows. So if you know linear programming, what I will now describe is just a linear relaxation of a standard integer program that would try to find a graph coloring, ordinary graph coloring. So what it is. So take your graph G, list all the independent sets you have there, all the possible color classes you can think of. To each of them assign some non-negative weight, maybe 0, maybe some positive weight, and find an assignment such that the following holds. Whenever you look at a vertex V and you sum up the weights of the independent sets that contain this vertex V, this sum will be at least 1. So if you think what the coloring is, you can think that you assign the weight 1 to your color classes, which are independent sets, and 0 to all the other independent sets, and then indeed each vertex V, if you look at this sum, the sum will be equal to 1. But now we just take a real relaxation of this integer program, and then what is the fractional chromatic number of graph G is just the minimum total sum of all the weights that you used for such a coloring.
The weights are the variables, and for every vertex you get one constraint.
Yeah, if in the linear programming language, that would be exactly as the program would be exactly as you described. And then if one uses the duality of LP programming, it can be derived that whenever I take an assignment of weights to vertices, I will always find an independent set which has at least 1 over chi f of the total weight. So, well, okay, just for this statement, I even don't need LP duality. This will just follow from some simple averaging argument. But using LP duality, one can show that on the other hand, if for any assignment of weights to vertices, I will find an independent set which is at least that heavy, then my fractional chromatic number is at most 1 over chi f. So it's real if and only if. And then let me maybe state one more definition. So, and this definition is the one that I was talking about on the first slide. And then yet another possible definition out of many possible definitions of the fractional chromatic number goes as follows. So take an interval from 0 to x, and to each vertex V assign a measurable subset of your interval that will have a unit measure. And now, what you want that if I look at vertex u and v and I look at the set that was assigned to the vertex u and the set that was assigned to vertex v, those two sets will be disjoint. And then what I would like to take, well, I would like to take as short interval as possible. So for instance, if I will be given a graph whose normal chromatic number is say 4, I can take interval of the length 0 to 4, split it into four unit intervals that are consecutive, and each vertex will get the interval that is kind of driven by its color in the ordinary coloring, and that's an okay coloring in this definition. But maybe I can do more. I don't need to take the intervals consecutive. The only condition that I need to satisfy is that the intervals are measured. So maybe let's look at rather than stating yet another definition, let me look at an example. So an example for me today will be a pentagonal prism. It has chromatic number 3, for instance, because of this 5 cycle. But so it has 10 vertices, chromatic number 3. So the independence number is at least 3. But in fact, there is an independence set of size 4. For example, this one. And if you take 5 copies, if you take like 5 rotation of this independence set of size 4, you can find the following. You can find 5 independent sets such that each vertex lies exactly in 2 of them. Like this red one, purple one, blue one, black one, and green one. So, for instance, in this definition, to each of those 5 independent sets, I would assign weight 1/2. And in total, the weight that I spread it around was only 5 halves, so 2.5. I saved 0.5 compared to the normal chromatic number. Also, I can think that I will take my interval from 0.25, from 0 to 2.5. I will split it into 5 bits. Each of them will have like 0.5, and then each of the vertex will take exactly 2 of those intervals. Does that make sense? So, okay. Before I move further, let me just maybe mention once more that all of this notion was actually established as something that should have either provided more evidence to four-color theorem at the time when it was just a conjecture, or disprove it. And in that paper, when it was established, and now I forgot the names of the people, I think it was Hilton, yeah, I don't remember now. Nevertheless, the guys what we are able to show is that every planar graph is strictly less than 5 fractionally colorable. So it was like an evidence that we might have hoped for color theorem. And it was done in like mid-70s. Okay. So let me now move back into this business between graph colorings and independent sets. So as I said, four-color theorem says that whenever I have a planar graph, then its fractional chromatic number is at most 4, and the independence number is at least n over 4. But there is another theorem about coloring planar graphs, which got quite famous, namely the Grech theorem, which says that if I have a planar graph but there is no triangle, then actually in the ordinary chromatic number I can save 1 more. So such graphs are actually 3-color. And in 1976, Albertson, Bolobach, and Tucker conjectured, so a particular corollary is that the independence number is at least n over 3. But Albertson, Bolobach, and Tucker conjectured that you can do always at least a little bit better than a corollary of 3-color theorem would tell you about the size of independent set. And it was roughly 20 years later, finally confirmed by Steinberg and Tuve, who showed that you can always do slightly better, but already like 10 years in between the proof and the conjecture, it was observed that you can never hope for more than just this a little bit. However, However, in this paper, Albertson, Volec, and Tucker conjecture that if I additionally restrict the maximum degree, and I will say that my maximum degree is at most 3, so quite often in the literature graphs of maximum degree at most 3 are called subcubic. Then compared to the kind of the small improvement, you can do much better improvement. You can get independent set of size that is like larger, like that has larger proportion, not just a little bit more, not just one more. And this conjecture, it took some while, but was actually confirmed with the best. Yeah, and it was known already that the best constant you can hope for is 3/8 in such a statement. So this was confirmed by Heckman and Thomas in 2006, and they conjectured that actually not just the independence version of this problem should be true, but also that the fractional version of the theorem should be true. And here is, for example, a graph on 8 vertices, which would kind of say, oh, this 3/8 is the best possible, and now if I would start gluing along those vertices of degree through more copies of this graph, you even see that like it's not just like some small issue with this 3/8, but really I cannot hope for a better ratio than 3/8, even in an asymptotic way, in an asymptotic sense. Okay. So again, there was this question of Albertson, Volec, and Tucker, which was proven by Heckman and Thomas in 2006. However, already in 1979, if you recall that like Albertson, Volec, and Tucker were asking for a better ratio than 1/3, Staton showed that fraction 5/14 is possible. And in fact, you don't need to assume that your graph G is planar. Just take any graph G that is triangle free and has maximum degree 3, then your independence number is at least 5/14. Then roughly 11 years later, Jones found a simple proof of this statement, and roughly yet another 11 years later, Heckman and Thomas found very much simpler and very nice proof of this statement. And also, they conjecture that the fractional version of Staton's theorem should be true. And roughly yet another 11 years later, me, Zdenek, and Jean-Sebastien look at that question, and this is the question I would like to focus on in the rest of my talk. So, are there any questions? Okay. So, one more remark. In 2009, shouldn't you show that if you have a triangle-free graph of maximum degree 3, unless it's a Peterson graph or the graph coming from the dodecahedron, you can always find an induced bipartite subgraph that has size at least 5/7. So it also gave yet another proof of the Staton result, because, okay, for those two graphs, maybe you need to do it by hand, but otherwise you take your largest induced bipartite subgraph and you take the larger color class of your bipartite subgraph. And by the theorem of Zhu, it will have size at least, the class will have size at least 5/14. So, that was the theorem of Staton, and already in the late 70s, it was known that you cannot hope for anything, for a better statement than 5/14. For instance, you take this C7-like addition of Peterson graph, or there is one more graph on 14 vertices. And both of these graphs have independence number exactly 5. Okay. So, as I said, this is the conjecture I would like to focus on. So maybe let me read it again. You have a triangle-free graph that has maximum degree 3, and you want to show that the fractional chromatic number of this graph is at most 2.8. So, before we start working on that question, there was already quite some progress on this question. In 2009, Hatane and Zhu showed that the fractional chromatic number is at most, of these graphs, is at most 3 minus 3/64, and it was the first result when the fractional chromatic number of triangle-free graphs of max degree 3 was bounded away from 3. Then it was improved 3 years later by Liu and Peng, and very recently there were also 2 improvements, one due to further improvements, one due to Ferguson, Kaiser and Kral, and one due to Chung-Hoon Liu. And in this talk I want to present a full solution of this problem. So before I move to, let's say, a proof sketch or proof ideas behind our proof, let me recall a proof of Heckman and Thomas for the non-weighted case for 2 reasons. A, it's a very nice and short proof, and B, actually our proof can be viewed that we try to follow the same strategy as Heckman and Thomas, just we needed to make it a little bit more involved to deal with the weighted case. So anyways, so this is the statement I would like to show. The independence number is at least 5n/14. And what is the idea of Heckman and Thomas? Well, use induction, but prove by induction a stronger claim. And since this claim will be stronger, maybe it will make my induction step much easier. And if somewhat like all of this will kind of clash together in a nice way, I might obtain a very simple proof. So what's the particular proposal of Heckman and Thomas? The proposal is following. Try to gain something extra from vertices of lower degree. So let's V3 be the vertices of degree 3, V2 of the vertices of degree 2, V1 of the degree 1, and V0 the isolated vertices. So the original conjecture says that for each of these vertices I would like to obtain 5/14 contribution to my independent set. But maybe for vertices of lower degree I can get 1/14 extra for each of the degree that they are missing. So, like, why would this be a very, very useful induction statement? Well, let's look. So, just maybe but rather for technical reasons than for some substantial reasons, let me assume that the graph is also C4 and C5 free, and every vertex has just degree 3. And let's look how I would proceed with my induction. I would look at any vertex V. It needs to get 5 units. So I remove this vertex, also I remove its neighbors. And I apply the induction statement. But in the induction statement I get 1/14 extra units for each of those 6 vertices in the second neighborhood of vertex V. So take the independent set from the induction hypothesis and add vertex V, because all of the neighbors of V were deleted, I can freely add the vertex V to the independence. And now just do the math and use this 6 times 1/14 extra coming from the second neighborhood, and all of a sudden you realize that this would be exactly what you would, this would be like exactly your goal. So this induction hypothesis would work amazing, like this stronger induction statement would work amazingly if it would be true. Unfortunately, it's not true. So for instance, you can take a 5 cycle, and here you will be, if you do the computation, you are 2/14 off. You can also take this K4 with a perfect matching subdivided twice. You will be off by 2/14. You can also take 2 copies of those graphs, join them by a bridge, again do the computation, it's 2/14 off. But whenever you start playing with those reasons why this statement is not true, you realize that it's 2/14 off. So an idea would be, well, let's just look how many components have this structure that I just described, and subtract 2/14 for each of them. And it's still fine, because in each such component I will find at least 2 vertices of degree 2, so I gained at least 2/14 compared to my original statement, so I will still at the end of the day, in the total sum, stay above 5n/14, and maybe this is a statement that I can push through induction. Yeah, so this is what I just described. I will subtract 2/14 for each such bad connected component. And it turned out that this statement is in fact true, and it maybe increased the length from having one slide long presentation to like 2 pages. Let me not describe all the details, but like from now on, the reasoning is relatively standard. You consider smallest counterexample.
What are the bad components? It's just component that is a tree of this.
I didn't describe it completely precisely, but you are right. So whenever I would have like block decomposition in a component, and each block will look like that, and they will be connected by an edge.
Okay.
So I can, like I said, I could have taken this one and this one, joined by them by a bridge. Now maybe I can take this vertex and this component, and again take vertex of degree 2, take a vertex of degree 2, draw an edge, and I can like build any tree-like fashion of this.
So block decomposition consists of edges and these.
Yeah, I maybe don't want to go into I think you have exactly the right intuition, but I don't like, it's rather technical than like enlightenment. So then kind of the template of a proof of such statement would go as follows. You take a smallest counterexample that would not satisfy this formula. You show that, oh, a smallest counterexample actually cannot have any of those bad components. It cannot have any vertex of degree lower than 3, and so on and so on. And then at the end of the day, you arrive exactly to the picture that I described at the beginning as kind of like motivation why maybe such a statement would be useful to show. You take vertex V, you remove the vertex V and its neighborhood, you apply induction, and you put vertex V back, and that would contradict the fact that G was the smallest counterexample. Does that make sense? Okay. So what would we do for the weighted version? So similarly to Heckman and Thomas, we try to prove a stronger statement, and it's very much motivated by the previous non-weighted formula, but this time you need to deal with the weight. So for each vertex of degree 3, you want to gain 5/14 of its weight. For each vertex of degree 2, you want to get 1/14 extra, and so on and so on. And again, there is some subtraction for the bad components. And the bad components are still the same, they are still having the same structure, but this time you need to consider the weights. And so like the philosophy is exactly the same, but maybe just to keep this talk simple, for the rest of the talk, let me ignore this. Like, it's a technicality you need to deal with, but it's not a substantial problem for the ideas. So this is the formula we would wish to hold, and again our goal will be to follow the standard proof template. We consider and we try to show that we can always make G smaller, use the induction, and then recover the large independent set in G, contradicting the fact that G was smallest counterexample, or G was counterexample at all. So first of all, let me focus on the case when the graph is irregular. And again, just for making my formula simple, let me also assume there are no 4 and 5 cycles, so the second neighborhood of a vertex really look like it. So for each vertex V, let me define kind of a potential function which is driven by this formula, and if this formula looks like that it falls from the sky, let me explain it. Let's now take it as granted, and I will explain in a minute how one can come up with this formula. So this is kind of a potential defined at a vertex V. So what will be our idea? Our idea would be, well, let's remove vertex V, let's remove its vertices, apply the induction hypothesis to get a weighted independent set on the remaining graph G prime. Let's take the independent set from the induction hypothesis and add the vertex V. So, and what is behind this formula? Well, this formula GV exactly describes what is the difference between the weight of independent set that we obtain with this procedure and the weight of independent set that we are asked to find. So why is it so? So if you look how much does vertex V contribute to the independent set I that we just constructed? Well, it contributes with the total weight of the vertex V, but I needed only 5 over 14. So I have 9 over 14 extra of the weight of V to kind of use as my profit. On the other hand, the formula says I should get there 5 over 14 also contribution for every vertex U1, U2, U3, but I put there only 0. So I'm missing 5 over 14 for each such vertex. And on the other hand, from the induction hypothesis, I saved 1 over 14 on each vertex x1 up to xx, up to x6, but in my original graph G, I don't need this excess of 1 over 14, so it's again playing in my favor. So in particular, if I would find a vertex GV, where GV is non-negative, I would use the induction on vertex V, and I would be fine. But now look, if I sum this formula GV over all the vertices in my graph G, no matter what are the weights I'm claiming, the total sum is 0. Why is it so? Each vertex V appears exactly once as the root. That's 9. Exactly 3 times in the first neighborhood. That's 9 minus 3 times 5. That's minus 6. But also 6 times in the second neighborhood, which is plus 6 times 1 over 14. So the total sum of all those GV is 0. So just by a simple averaging, there must be at least one vertex when this formula is not negative. And the induction on this vertex will be 1. Does it make sense?
So this is again using C5?
I mean, not substantially, because then I would just identify those vertices. Again, it's rather technical. I want to keep it as a plan, and like if I tell you this plan, you would make it into rigorous proof with some effort, but you would not require it.
I see that you get one more extra there.
Exactly. So just for the simplicity, let me draw it like this. So, in fact, what makes the problem, like what was the biggest trouble in this in like finishing argument along this line were not vertices of degree 3, but vertices of degree 2. But before I move to vertices of degree 2, let me just as a warm-up say what we do with vertices of degree 1. Oh, I also have to say I completely ignore vertices of degree 0, but it's not that hard to put into a weighted independent set at least 8 over 14 of the weight of them. In fact, I can just freely add them and get 14 over 14 contribution from them. So anyways, what do I do with vertices of degree 1? So this is the weighted variant of stating what is my goal, what is the problem I need to deal with. But let me also rephrase it into the coloring scheme. So usually a coloring, what it means, or fractional coloring, it means that I have this interval from 0 to 14 over 5, and each vertex I would like to assign a measurable subset of unit length of this interval. But since I want a little bit more weight, if you just do the fractions between the weights, it means that on vertices of degree 2, I actually want to have stronger coloring. I want to assign them vertices. I want to assign them sets of measure 6 over 5. I want to get another 1 over 5 for vertices of degree 1, and so on. So what do I do with vertices of degree 1? Well, so either they form a completely independent edge, and then I just look, oh, which of the two weights is bigger? Does W1 or W2 bigger? And then I put into my independent set the heavier vertex of those two, and of course that one will contribute with 7 over 14, and for the rest I have also 7 over 14 that I didn't use from W1, and it will easily pay back for the W2. Or another thing is that there is a vertex of degree 1 connected either to vertex of degree 2 or of degree 3, but now I remove this vertex, I apply the induction, I get either 6 over 5 or 7 over 5 subset on the neighbor, but since my total length is 14 over 5, I will just take the complement of the color that was assigned here, and it will have measured at least 7 over 5. So this is not so enlightening as a statement, but like I just wanted to set up my mind in what arguments I might be using for vertices of degree 2. So let me now move to vertices of degree 2. So let me tell you like 2 out of 3 possible cases. The third case I will ignore because it's maybe the most technical. And again, my aim is to rather like give you a full proof, to give you a flavor what are the arguments that we are using. So the first case is the following. Suppose I have 3 consecutive vertices of degree 2, or at least 3, but on the picture let me just show what I'm gonna do with 3. Then I'm claiming it's again very easy to find a reduction like for the vertices of degree 1. How? I will remove the middle vertex and the 2 neighbors. So I apply the induction on the remaining graph, and here I get 1 over 5 extra. Now put to the middle vertex a measurable subset of 0 to 4 of the interval that intersect this one on at least 3 over 5 and this one on at least 3 over 5. Just for simplicity, let me just consider the worst case when they really intersect on, like this purple one intersect on 3 over 5 here, exactly 3 over 5, and this blue one also intersects on exactly 3 over 5. If the intersection would be bigger, that's just better for my job. And now, what is my aim? My aim is, so I have here the 6 over 5 because this vertex has degree 2 in G prime, but in fact I can easily remove 1 over 5 measure here and 1 over 5 measure there, and it will still be fine for the original graph G. So let me do so, and let me do so in a way that still I keep this intersection as I want. And now what is my goal? My goal is to find 6 over 5 subset of the coloring interval for this vertex and also that vertex. So let me maybe argue about this vertex, and this one will be completely symmetrical. So my total length is 14 over 5. I spent one unit on this vertex. I spent totally 6 over 5 unit on this vertex, but I double counted this purple part. So let me put the double counting back, and if you just do the math, all of a sudden I have 6 over 5, at least 6 over 5 completely free to put on this vertex. Is that fine? So the last case I want to touch is the one when I have one vertex of degree 2 and both of its neighbors have degree 3. So then I don't have a single argument how to deal with that, but I need to do some cases. So one case would be, let's remove V, U1 and U2, apply the induction about weighted independent set on the remaining graph G prime, then maybe analyze few cases, but they are rather simple, and you realize that everything is fine. You get your independent. So okay, I apply the induction on this remaining graph G prime, and to the independent set from the induction, I freely add the vertex V. So this strategy would work perfectly if there is some relation between the weights of the vertices V, U1, U2, and the remaining neighbors of the vertex U1 and U2. So if such an inequality between the weights would be satisfied, I'm in a good shape. So what do I do in the other case? So let's try to use the other induction hypothesis we have, the coloring induction, the coloring hypothesis rather than the weighted independent set hypothesis. So I remove the vertex V, just the vertex V, and I get the coloring from the induction. So these were the neighbors of vertices maybe get measured. Maybe they have also degree 3, I don't know, but let's say they do. So there I spent there I needed to place subset of measure 1, but on those vertices I gained this 1/5 extra. So I have 6/5 here, 6/5 here, so I can freely add here 2/5 that is completely disjoint from blue and purple, and also I can take 1/5 from here and 1/5 from here and add it to this blue. So I obtain this coloring, which is quite far from my goal, but maybe because maybe the weights between those vertices are such that I would get a good weighted independent set, and it would end up that weighted independent set would enable me to reshuffle the color. So in other words, I look what happens if I have this sort of coloring, and I try to extract the independent set. Is that independent set any better than the one that I would like to obtain in my ultimate goal? Yes. Yes, in the case that there is some, again, inequality, like mutual relation between the weights on this picture. And it might look like a magic, but those two formulas are exactly complementing each other. So the goal is that if I have a vertex of degree 2 with two neighbors of vertex of degree 3, what I'm gonna do, I will think whether this or that relation holds between the mutual weights, and either apply this strategy or that strategy, but in both of the cases, at the end of the day, I will be in good shape. Any questions? So I think that's all what I wanted to say about the proof. So with like more rather technical and case analyzing work, but roughly speaking, following ideas of this type, one can eventually conclude that like all of the issues can be handled, and at the end obtain the statement that whenever you have triangle-free graph with maximum degree with maximum degree 3, then the fractional chromatic number is at most 2.8, which confirms the question of Heckman and Thomas. So there is also the planar conjecture of Heckman and Thomas, which was saying that you take a planar graph G, and then in fact you can show that the fractional chromatic number is at most 8/3, so 2.66666 instead of just 2.8. And as far as I know, the best result for the planar conjecture is actually our non-planar conjecture, saying that it's at most 2.8. If one could think that what we did is that we took Heckman-Thomas proof for the general case and try to put it into the weighted setting, then why don't you try to take the proof of Heckman and Thomas for the planar addition, for the planar statement, and try to push through the weights. So unfortunately, we don't see how to make it for two reasons. One, the non-weighted proof of this was like about 2 pages, and our proof is about 20 pages. And if you just use the numerical magic, since this was like 26 pages, maybe the way how to make a weighted proof of this would be 260 pages. But even if you don't believe in like magic, oracles, and numerology, one of the things that Heckman and Thomas used in their proof was that if you have an independent set and you look at its size, it's always an integer. Well, sure, it is. It's just number of vertices such that something. But once you deal with the weight, and at some point they proved some bounds that were non-integral, and then they say, oh, freely we can round it up. But in the weighted case, such an argument is immediately ruled out. You cannot freely round up to the nearest integer. So right now we don't know what to do for the planar conjecture. Also, I showed you two graphs, They had size 14, they had independent set exactly 5, saying that you can never hope, in this statement you can never replace this 14 over 5 by anything bigger. However, Jones and even in the non-weighted case. But Jones and Locke in 1995 showed that if you have a connected graph G and you look at its independence number, it's not only like if you allow me some lower order error, then the fraction is bigger than 5 over 14. Actually, it's 11 over 30. And also, if one just plug the numbers in, it shows that whenever you have at least 15 vertices and your graph is connected, you can do a little bit better than 5 and over 14. And then the natural question is like, can you also make this Jones and Locke result? Can you also put Jones and Locke result to the weighted case? Well, we don't know now. And even if I would, so the precise reformulation of this statement would allow you error in the fractional chromatic number of order 1 over n. But even if I will be more modest and allow you any error that tends to 0 for large graphs, we don't know. And also, one last thing I would like to mention is I told you at the beginning about Greg's theorem, which says that chromatic number of, so it says that the triangle-free planar graphs are 3 colorable, so they are also fractionally 3 colorable, just like from it just immediately follows from the definitions. And I also told you that Jones showed that for the I stated here in the weighted case, but in fact what Jones showed that there always exists a planar graph without triangles where either you take this as your fractional chromatic number, so it will be strictly less than 3, but never bounded away by 3 by some absolute constant. And in fact, she didn't show it for the fractional chromatic number, she showed it for the independence number, so in the non-weighted case. So it kind of rules out any possible theorem which would say triangle-free planar graph has fractional chromatic number at most 2.99999, but still maybe you can say if you have a finite planar triangle-free graph, its fractional chromatic number is strictly less than 3. By the factor that depends on G, but maybe depends on the size of G, but it's strictly bounded away, but it's below 3. And that's what the methods that we used for this theorem, together with some structural results that are actually mainly coming from Bernard and Zdenek, that's what we were able to show. So, and here one can see that the bounds between the construction of Jones and our upper bound are just by factor of 3 from each other in the error tag. So yes, the answer to this question is finite triangle-free planar graph colorable with less than 3 colors in the fractional sense is true. And with this, I anyways run out of time, so I would like to thank you for it.
Thank you. Are there some questions? Do you know what is fractional color? Maybe. Let's thank Jan again.